you. So we just have one more question, and so let me answer this partly because maybe this will be a question several people have on their minds. So the question was, why don't I have a choice of boundary conditions? You know, so I said, well, they're either periodic or antiperiodic. If you don't have a choice, you must have this. So why is this? Well, the reason is because we chose in the first instance the boundary conditions for the spins. We said the spins have periodic boundary conditions. Once you fix this, and I did this, then the boundary conditions for the fermions are given to you. There is no choice. Of course, now, you know, so this being a free country, you might say, well, okay, I don't really want to have periodic boundary conditions on my spin. Let me put twisted boundary conditions or whatever else you like. Yeah, or open boundary conditions, that's perfectly fine. So the same kind of mapping will go through and will give you some particular boundary conditions for the fermions. Okay, but once you fix the boundary conditions of the spins, there is no freedom. Now, why do I work with periodic boundary conditions? Well, I work with periodic boundary conditions because I like translation invariance. If I don't have translation invariance, life is bad. Yeah, so because it's more complicated. And so, for example, the types of things I'm going to derive next, so they are simple because translational invariance is built in. Yeah? So on an open chain, yeah, so if you have a quantum spin chain which looks like this, yeah, then, as all of you know, if I calculate the correlation function, it does not only depend on the distance between 2 points. So if I have a spin here, and if I have a spin here, the correlation function does not only depend on the distance between them, but also on the absolute position. So it's more complicated. Yeah? Whereas on a ring, the 2-point function will only depend on the distance between the spins, so it's easier. That's why we work with periodic boundary conditions. You can do open, but it's harder. And actually, everything I'm going to tell you, you can do for open boundary conditions if you want, but it's more work. Alright, so I will do periodic. And you can do open as an exercise, because you have so much time in the afternoons to Alright, so what I want to do next is, still in the context of this free theory, I want to calculate something, it's a little bit perverse, so I will calculate the spectrum of low-lying excitations, the energy spectrum and the momentum spectrum for this model of non-interacting fermions. Okay? So why would I want to do that? There's a reason for it. So the spectrum, you will see, has a characteristic form. And it has a characteristic form which is related to conformal field theory, which is, and what we want to do in the end of the day, we want to use methods from conformal field theory to work out properties of this Heisenberg model when you have interactions. And the form of the finite size spectrum is characteristic for the critical theory you have, and so it's useful to work it out for a case where it's easy, and that's what I'm going to do next. Okay, so I will take L even, as I said before, and I will work at a density D, which is n divided by L, which I keep fixed. Yeah, and the density I tune by this applied magnetic field. Okay? But I will work basically now in a canonical ensemble where I fix the density. And the density is fixed by this requirement, epsilon of plus minus kf is equal to 0. And this, as I said before, is j cosine kf is equal to h. Yeah, and then kf, so this is equal to 2kf. Okay, so these are all just properties of free fermions, because what I've done is I have filled the states between minus kf and kf. Yeah, they are equally spaced because it's a free theory, Therefore, the density in the ground state is literally just 2kF. Alright? And kF, as we said before, is determined by my dispersion of elementary excitations becoming gapless at these points. Alright? Okay. So this is just okay. Now let's start with the ground state energy. So E0 is the sum from little n running to minus n minus 1 over 2, n minus 1 over 2. I have to tell you one more thing which I didn't do, which is whether n is even or odd. So I take n to be odd. Okay? So that means my magnetic field is such that capital N is odd. And I just start with this, and I will tell you what happens in the second with even n later. Okay, so now let me start by calculating the ground state energy. So it's just minus j cosine kn plus h. Okay? So ground state energy is just this bare energy of all the negative energy states. Right? Now, all of you should know how to calculate such sums. So you do this by turning them into integrals by using this Euler-Maclaurin sum formula. Okay, let me just remind you what it is. So little n is n1 to n2, f of n over L can be written as an integral from n minus over L to n plus over L dx f of x. And then I think it's minus, so there's a typo in my notes, 24L squared f prime n minus over L minus f prime plus over L plus over L. Okay? So this is, I'm not sure about the sign, I forgot whether it's plus or minus. So this is just a way of turning a sum into an integral. You have a question? No? Alright. Where n minus is n1 minus a half, and n plus is n1 plus a half. Plus dot dot dot, yeah.
Yeah, sorry, can you just comment what does this field Fermi C mean in terms of spins?
Well, no. So in terms of spins, this is something complicated. Yeah, if you think about it, because in terms of spins, what you're thinking is you have a picture which is naturally located in real space. Yeah, you have spin up, spin down somewhere. But what the Fermi C means, the easiest way to understand it actually is to go back to Martin's lecture. So he told you what the wave functions of eigenstates look like, or he will tell you, I don't know whether he studied already. So these are superpositions of plane waves. Yeah? That's precisely also what the Fermi C looks like. Right? So it's a Slater determinant. Yeah, this will Fermi C, the wave function would be a Slater determinant. If you expand it, you see it's a superposition of plane waves with simple coefficients. Yeah? That's what it looks like in terms of the spins. Yeah? So it's the spins, the down spins, essentially propagating like plane waves and superposing like crazy.
Yeah, but the limit where you have zero density, that's where you have...
Yeah, so the limit when I have zero density, I have fewer and fewer down spins. Yeah? And eventually I just have two down spins. Yeah? So then I have just two particles. Eventually I have zero down spins. And then I have up, 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 and then I've reached my transition. Alright? Okay, so it's not so, I mean, and of course if you're away from delta equal to 0, things are much more complicated. Yeah? Euler-Maclaurin, yeah, so plus dot 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 means what? Well, it means terms of higher order in 1 over L, yeah, which are not interesting for us. Okay, so now we can use this to turn this into an integral, so let's do it.
So n plus is related to n1 or n2?
Thank you very much, it's actually an integral. So essentially what you do is you have to, the integration boundaries are moved by half spacing between these ends. Yeah? And if you use this, yeah, then the corrections are actually 1 over L squared. If you don't do this, if you choose these integration boundaries naively or whatever, you get actually corrections which are 1 over L. Yeah? So these are chosen already in a kind of cleverish way. But this is a standard case. All right. So now plug it in here, and what you find is this becomes L times the integral minus d over 2 to d over 2 dx minus j cosine 2 pi x plus h minus j pi over 6L squared sine pi p plus dot dot dot. Okay, and now this is L times the ground state energy density in the thermodynamic limit, which I call E infinity. Yeah? E infinity is the energy per site in the thermodynamic limit, yeah, which is what I have here. And then you have a correction, and the correction is most easily expressed in terms of the thermal velocity. This is pi Vf over 6L, and then plus order L to the minus 2. And Vf is the thermal velocity. So thermal velocity is like so. You have your band. Yeah. If you calculate the group velocity here, yeah, that's so epsilon prime of Kf. That's Vf. Yeah. And so this is J sine Kf. So now, those of you who like conformal field theory, they will be happy because they will say, aha, so this is exactly the correction to the ground state energy you expect for a conformal field theory in a finite volume with periodic boundary conditions. Yeah? And what you have for conformal field theory, you have a thing here that's also proportional to the central charge of the theory, which is called C. And this basically tells you that this free fermion theory is a conformal field theory with central charge 1. Yeah? But let's take this away. Right, so that's the first thing. Now, what about the momentum? The momentum of the ground state is clearly 0 because my Fermi sea is filled symmetrically. Okay, so I have energy is this thing, and momentum, so P naught is equal to 0. Okay, so this was the first exercise. And now what we want to do, we want to calculate the complete spectrum of low-lying excitations, yeah, in this theory. And there's a lot of information in that. So in particular, once again, those of you who know conformal field theory, from that spectrum of energy and momentum, we can read off all of the conformal dimensions and the conformal spheres. So how do I do that? Well, I use essentially now the fact that the dispersion is linear at low energies. Okay, but before doing that, so a completely analogous calculation gives the lowest energy in the sector with n plus L fermions where L is even. Is that clear to you? So what I do now is I do exactly the same calculation. I just change the fermion number by an even number. So for example, rather than filling all the states between minus kf and kf, I can consider the state now where I have an extra particle here and here. But the lowest energy state would be always symmetrically filled, so to speak. So this would be little l is equal plus 2. And then I just use my Euler-Maclaurin in some formula, go through the same calculation, get an answer. I can also take off two particles, make two holes here, do the same calculation, I get an answer. And because I take L to be even, I remain in the same sector with the same boundary conditions. So the total fermion number remains odd. Okay? So the answer that comes out here is EL is E naught plus pi Vf over 2 capital L, L squared plus dot dot dot. Okay? So now, and the energy is this, sorry, and the momentum is still 0 because all of these states are symmetric. Okay, so now we are almost there. Now, any other excitation with n plus L fermions is obtained, and L is even, still even, by making additional particle-hole excitations. That's kind of clear, because I don't want to change the particle number, so all I can do is I can redistribute now these particles, and I must stay in the low energy sector, so I will stay around K plus minus Kf, where the dispersion is linear. Okay? And then what I will do is I can make, for example, a hole here, and make an extra particle here. That would be a particle-hole excitation around Kf. I can do the same here. Okay? But I also can make excitations which are so. I can make a hole here and put the particle here. Yeah? And that excitation has a different nature. Because here, particle-hole excitations, they don't cost momentum. So the momentum will be microscopic. It will be proportional to 1 over L. Whereas here, momentum transfer will be proportional to 2 Kf, which is macroscopic. Okay? So essentially, this will cause a finite amount of momentum, and this basically an infinitesimal amount. Okay, so now all of these, I can calculate the energy, and it will have the form that I get, first of all, the lowest energy state in the sector with n plus L fermions, which I call E sub L. And now I add the energy of particle-hole excitation. So I make particles and holes. So that will be the energy. Okay? Because the spectrum is additive, it's a free theory. Alright. And now you finally use that epsilon for k is approximately plus minus kf is approximately linear, so that's Vf k minus plus kf plus order 1 over L squared. Is that clear to you? Why is that? So if you look at this, what is the order of this? The order in 1 over the system size. It's 1 over L. So why is it 1 over L? Well, okay, so it's 1 over L because right, the momenta around Kf, they are quantized, and they are quantized in units of 1 over L. Alright? So now the dispersion here is linear, so that basically means the energy is proportional to the difference in momenta. Okay? But the difference in momenta, if I stay close to here, will always scale like 1 over L, because the momenta are integer divided by L. Yeah? And I consider the difference of integers, which is order 1. Yeah? So this indeed will be order 1 over L. Yeah? And where does this come from? Well, okay, so I can just expand the dispersion in a Taylor expansion. So I start linear, and then I have other terms, quadratic, cubic, and so on and so forth. And by the same argument, because the difference of momenta scales like 1 over L, these terms will scale at least like 1 over L squared, which is beyond the accuracy that I'm aiming for, because I'm aiming for accuracy 1 over L. Right, now you plug this in here, and then find the following answer. So L E infinity plus 2 pi df over L squared over 4 plus n squared plus m equals 1 to infinity m plus n minus m plus order n to the minus 2, and the momentum is 2kf times n plus 2 pi over L sum m equals 1 to infinity m plus n minus m. Those were the equations I was after. So still, total Fermi number is always odd here, now, you can recognize the various states we have considered. So if I look at the lowest energy state in the sector with n plus L fermions, so the contribution is L squared over 4. So L basically tells you the change in particle number compared to the ground state. Okay. So then this integer n basically tells you, if you look here, how many particle Hall excitations of this type you have made. So how many particles you have backscattered across the Fermi sea. Yeah? So this is a quantum number, that's a quantum number, integer quantum number. And then these guys basically enumerate all particle Hall excitations around Kf or minus Kf. So particle Hall excitations of this kind. Alright? And so what is what? So this n sub m is essentially the number of particle Hall excitations of type m around Kf, and minus m would be the number of particle Hall excitation around minus Kf, and this number here basically tells you the nature of the particle Hall excitation. So what I mean by that is, here's my linear dispersion, here's Kf, and my momenta are quantized, so this is the grid of momenta, okay, and this little index m basically tells you the momentum transfer. So if I make the hole, here and the particle here, so to speak, then m would be 1. It would be a particle Hall excitation which costs me the minimum quantum of momentum. Okay, but I also could basically do things differently. I could say let me make the hole here and put the particle here. Yeah? And then you see there's a large momentum transfer, and this index basically tells you what is this momentum transfer. All right? Okay. So now we're almost done. Okay, so first of all, this 1 over L part of the spectrum here and the 1 over L part of the spectrum here are once again, so they are characteristic of conformal field theory. So what you can do by having this, you can read all the scaling dimensions of operators are. Okay? So this would now allow you to fully identify what this conformal field theory is, and we'll see a little bit later what it actually is. As I already said, so center charge is equal to 1, but there are many theories with center charge equal to 1. And what it is, it's a compactified boson. It's a bosonic quantum field theory where the target space of the boson is a circle of a particular radius, which we have to calculate. Yeah? And we will make this identification basically on the basis of what I've just done here. Right, so this was when n, where the total particle number n was odd. What about the even sector? I haven't told you anything about that yet. And what you do in the even sector, you repeat the same analysis I've done for you before. So you basically start with the lowest energy state in the even sector, calculate the energy by Euler-Maclaurin, and then construct the excitations in exactly the same way you have done here. All right? What you find that the lowest energy state in the n equals to even sector corresponds to the same formula here, but with little l equal to 1 being odd. Yeah? So you get the same formula in the even sector for energy and momentum in the end of the day, but where now L is allowed to take any integer value. Before, by construction, L was always even. So I stay in the same sector. Okay? If you don't believe me, I mean, I can show you how it works, but you also can work this out for yourselves, I think. All right? Or do you want me to I think we have too many things we still have to run through. We have questions.
Are there restrictions on NM?
Are there restrictions on NM? Well, they have to be integers.
Well, yeah, but you can, if you look at the edge of the Fermi surface, you can only have 1 for m equals 1, for example.
Well, okay, so it's a little bit more complicated. So what you have to do is you have to work out how these particle Hall excitations can be described by these quantum numbers. So I can give you some examples. So let me say the ground state is this one. 1, 2, 3, 4, 5, 6, 7, and here we have zeros. So this would be the ground state. Yeah? And now I want to do particle Hall excitation. So the simplest particle Hall excitation would be this one here. Yeah? And that simply would be n1 equals 1. Okay? Now I can also look at n2 equals 1. That would be this one. This is plus 0, 0, sorry? Did I do something wrong? That's what I was thinking. No. So this would be n2 is equal to 1. And then you get the idea. So n3 equal to 1 is this one. Yeah. So essentially what we have done here are these. So you're happy with these. Yeah. So now what about n1 equals to 2? What does that look like? Okay. So that looks like so. Then I have plus, plus, plus. 1, 2, 3, 4, 5, 6, 7, 5. and then I have 0 plus 0, 0, 0. So that would be n1 equal to 2. And so basically what you need to do to get this, you take the ground state, yeah, which is this one. You first move this guy here, yeah, and then you move this guy there. You see what I'm saying? So you first make a particle Hall excitation exactly at the Fermi surface, and then you make a space at the Fermi surface for the next one to follow. Yeah? So this is how you get higher numbers of n1, n2, and 3. Yeah? So this parameterization that I've chosen here shouldn't be immediately obvious. So it parameterizes all possible particle Hall excitations, but you have to work a little bit in order to understand it, which is yet another exercise for this afternoon.
Isn't there a -1 in the formula for large P? Before the big N minus N.
This is a plus.
Well,
Sorry. Sorry. Yeah, thank you. It's a minus. Yeah, I think that's correct. Because it's in the other direction. I think that's correct, yeah. Thank you. Are there other comments? Umklapp excitations are these. Yeah. So once again, the spectrum is additive. So the two types of excitations you can consider separately. Yeah. And Umklapp excitations always must cost energy 2kF or minus 2kF. So you can read it off here. And these are just these guys. Yeah. Okay. Good. So that's the finite size spectrum of energy momentum. So it will help us to basically make contact now with field theory in the end of the day. There's a lot of information here already. As I said, so for those of you who know quantum field theory already, so now you could tell me precisely what theory it is. Yeah? For those of you who haven't done it yet, I will actually derive it for you. Yeah? But there's a lot of information here. Yeah? And we'll use it. But before we get there, now, so far I've worked with a lattice model, yeah, no field theory anywhere. So this is just the low energy spectrum of the lattice model. And the lattice structure is still kind of like strongly present, yeah, with this backscattering excitations. What I want to do now is, I first of all want to derive a continuum limit of my interacting fermion mode. So now we go to field theory. Okay? So far everything is still lattice. Okay? Now, the construction of the continuum limit is actually quite easy, to be honest. So what we do is, and I will do this for you now, not for the free theory, I do it straight away for the interactive theory. So we write this as H free plus H int. Yeah? And H free is not exactly what you think it is, so that's minus J over 2, sum over J, Cj over J, Cj plus 1 plus solution conjugate. And then here I have plus H minus J delta, but then I have an extra piece, plus J, 2J delta, and here I have the expectation value of Nj, complicated looking expression, sum J equals 1 to L Nj. And H int is J delta, sum over all J, and here I have normal ordered my interaction. So Nj normal ordered, Nj plus 1 normal ordered. And what this means, what these dots mean, so Nj is simply the operator Nj minus the ground state expectation value. where this is the ground state of the free theory. Okay? So this is, in a sense, a standard procedure. Yeah? Whenever you have a many-particle problem, yeah, which is interacting, what you do is you have the free part, yeah, which is there, which is this piece, and then what you have to do is you have to normal order your interaction to start with. That gives you an extra contribution to the free piece, yeah, which is this one. Okay, and then the normal order interaction. So now you already see there will be some self-consistency requirement in the end of the day, but we'll solve that. Okay, so now this one I call H prime. Just some chemical potential, some effective chemical potential. Okay, now we go to Fourier space, as we did before. Let me do this first, actually. Solve the free theory. Okay, so we do this by going to Fourier space. So we have the ground state of this free theory is once again a field from C. So K is less than Kf. C dagger of K on some appropriate vacuum, where now Kf, so what I will do now from here, because I'm about to take a continuum limit, I put back proper units. So what I did before for the lattice model, I wasn't working in proper units because, for example, my Fermi momentum was dimensionless. Yeah, but it's a wave number, it should really have dimensions 1/meter. So what I do now for you is I put in all the formulas, the lattice spacing, put it back. So A naught is the lattice spacing, which dimensions of meters. All right, and now this one will be a proper wave number, has dimensions 1/meters. And before, when I was working for the lattice model, I simply had set the lattice spacing to 1. Which is now no longer good enough because I want to take the field theory limit, which actually is the limit in which the lattice spacing goes to 0. So let me just do this. So first of all, this is by the same formula we had before, R plus cosine H prime divided by J. Okay. And the self-consistency is I'm supposed to calculate the expectation value of the density in my ground state, in this ground state. And this is just 1/L, sum J plus 1 to L. And J. We do it like this. Okay? Because I basically have translation invariance, that's what I'm using. And this is simply Kf A naught divided by pi. Yeah? Because the density is total particle number divided by L. And now you see we have a self-consistency equation because H prime involves this density. Yeah? So Kf is a function of this expectation value. So you get this expectation value is equal to some function of the expectation value. You have to solve it. Okay? And once you solve that, you find that what the Fermi momentum is, so Kf A naught, is equal to R cos H minus J delta plus 2J delta Kf A naught divided by pi, which is some kind of complicated equation for Kf now. But we can solve it using that this delta is a small parameter. Yeah? Because what we have in mind is we want to construct now the continuum limit in the vicinity to delta equal to 0. So we will use that delta as a small parameter. Alright, and then KFA naught is approximately equal to cos h over j minus delta divided by square root 1 minus h squared divided by j squared 1 minus 2 over pi cos h over j plus order delta squared. Okay, so that's the solution of the free part of the theory. So I went through this quite quickly, but it's not a complicated thing, right? Because the free theory, if we just call this h5, we solved before. Yeah.
You have to divide by j.
I have to divide by j what?
The bottom.
Bottom in the center.
No,
Bottom.
down in the
Left.
center.
Center, bottom. That,
Center bottom.
that one.
It's dimension.
The argument I mentioned for.
You just to divide by j.
By j.
Yes, just to divide by j. This.
Yeah, the argument.
Too.
Also, thank you. J. Okay, very good. Indeed. So now it's better. Okay. Now, Martin will calculate for you what Kf is, unbeknownst to him. But essentially, this quantity for the interacting case, so when delta is not equal to 0 and when delta is even not small, is related in a simple way to the magnetization per site. Okay? And the magnetization per site, you're going to calculate for them supposedly from Bedan Satz. Yeah? Maybe. Okay, but you can calculate this from Bedan Satz. So this is essentially the magnetization per site minus a half or something like this. So let's see. So this would be pi over 2. So 2 divided by pi Kf A naught is essentially related to the magnetization per site. Yeah? So it's something like this, which you can calculate from Bedan Satz. Now the interesting thing is, as it should, if you expand the full answer, the exact answer, in powers of delta for small delta, you actually get this series expansion of delta. Yeah? Which is as it should be. I'm just telling you these simple calculations connect in the way they should to things that you can calculate exactly. Now, let me...
A question. But is the magnetization per site because you want that to be the density of your fermions?
Yes, I mean, so essentially it goes simply like this. You have SZJ was like C dagger J, Cj, like minus a half.
Yeah.
In general. Yeah, so interaction or no interaction, it doesn't matter. So now magnetization per site is this, yeah, and this is the density of fermions, which is related to K.
Yeah, exactly. Yeah, exactly.
Yeah, that's correct. Anyway, that's an aside. That was just an aside. Now, we want to take the continuum limit, which is where we're going. But so now, we have first of all determined Kf, which is good. And now, we first of all take the thermodynamic limit. L goes to infinity, and then we write down what our free Hamiltonian is. So the free Hamiltonian is integral minus pi to pi dk over 2 pi epsilon of k c dagger of k c of k. Where now my canonical Fermi operators have the desired anti-commutation relations that give a delta function. Yeah, so that's how I had defined my Fourier transforms before. Okay, so now I work in the infinite volume, I get this. Epsilon of k is still the same thing we had before, so minus j cosine k plus h prime. Okay, and now what we want to do is we only want to keep in this momentum integral, we only want to keep modes when k is close to kf or k is close to minus kf. So let's do that. I just need another 5 minutes or so, then we can stop. So now the idea is keep only low energy modes. Yeah, and so what I do is I truncate H3 to these low energy modes. So I introduce a cutoff, which I call capital lambda, and then what you do here, this is your dispersion, yeah? Minus kf, kf, and here you integrate over the entire dispersion, everything. Now what we do is we only want to keep these modes, yeah, where lambda basically tells you in momentum space how far away from minus kf or kf you are. So I only keep in momentum space these two intervals. So then we write this. I think you understand what I'm writing as soon as you see it. So VFK, C dagger kf plus k, C kf plus k. And then I have minus VFK, C dagger minus kf plus k, C minus kf plus k. Okay? So basically, these modes are these. Okay? And the second line are these. Alright? And lambda, this capital lambda, it's a cutoff. Okay, so because now we go to the field theory limit, and the field theory always has to be defined here with a cutoff, yeah, because at the energy momentum or energy scale of this cutoff, the approximation of this lattice Hamiltonian by a field theory will break down. So for us, this cutoff is actually a physical energy scale. We can identify it on the basis of the lattice.
What about the sign? It should be
I think it should be correct, so let's see. So minus kf if it's positive.
No, this is okay. The k is the overall sign, minus vf or plus vf.
This I think is minus.
Okay, maybe
because you see here, if k is positive, I'm going here. Isn't that? Well,
it should be plus, I think. Well, I don't know, because you're destroying a particle in the Fermi sea, you're creating outside, so the...
Yeah, let's just check it. I mean, so this one is easy. So this one is correct because it's filled. So now, if I have this positive, yeah, okay, so I think...
Well, maybe I got it wrong.
So what it is? So epsilon prime of minus kf stands here. Yeah, and so that would be minus j k. No, I think it's correct.
Yes, maybe you're right.
I think the sign is probably correct. So we can. I will check.
I will check.
But anyway, so now one more formula before I let you go off. So this is what happens in momentum space. So I just want to write the analogous formula. Okay, so lambda must be such that Vf times lambda has to be much less than the minimum of epsilon of phi, epsilon of 0. Yeah, and that basically means lambda, which tells you how close to the Fermi point you are, has to be such that you don't feel that you're not in the vicinity of the minima or maxima of the dispersion, because there clearly linearization is not a good approximation and lattice effects are important. Yeah? Now, the last formula that I want to write is you can translate this formula that we have derived in momentum space to position space, and there it amounts to saying I take my lattice Fermi operator C sub j and I replace it by the square root of the lattice spacing. Yeah, that's just a convention, but it's a very useful convention, times R of x, a right-moving Fermi field. This will be our Fermi field, which is slowly varying on the lattice scale, times e to the I kfx plus left of x e to the minus I kfx. Okay? Once again, this is a smooth field, a slowly varying field. X is just j times the lattice spacing. And as I said, so these are Fermi fields, so they fulfill the usual anti-commutation relations. And what we will do in the next lecture, we will basically use this description here to derive now the low energy, the continuum limit of not just the free theory, but the fully interacting theory. Yeah? And what we will find, this will be Fermi field theory, yeah, 1+1 dimensions, with 4 Fermi interactions. Okay? And we'll do that next time. So thank you.
Other question?
They want to have their coffee.